Let's talk about the chemistry of alkynes. One way of producing alkynes is by dehydrating a vicinal diol. What we have over here is called a vicinal diol. We have hydroxide groups attached to adjacent carbons. And what happens is that the hydroxide group will run away with the hydrogen of the adjacent carbon and go away as water, forming a pi bond. And since we have two hydroxide groups running away with two hydrogens producing two water molecules, what we end up is the formation of two pi bonds, resulting in the formation of a triple bond. We can do this using the typical dehydrating agents: concentrated sulfuric acid 170 degrees Celsius, P2O4 delta, H3PO4 delta, Al2O3 350 Celsius, and dilute sulfuric acid delta. Another way of obtaining an alkyne is the dehydrohalogenation of a vicinal dihalide. Here, in the same way, the halide runs away with the hydrogen of the opposite carbon, the adjacent carbon, and goes away as a hydrogen halide, producing two pi bonds, which results in the formation of a triple bond. And we do so with the reagent alcoholic KOH. Now let's talk about alkyne reactions. These are the ways of producing alkyne, and now we'll be discussing how alkynes react. Well, one thing we can do with alkynes is hydrogenation, catalytic hydrogenation. Actually, we can partially hydrogenate alkynes into alkenes, or we can fully hydrogenate it into an alkane. If we want to fully hydrogenate alkyne, we do so with hydrogen gas while heated with a catalyst like platinum, palladium, and nickel. The catalyst gets stronger to the right direction. We can use Lindlar's reagent to partially hydrogenate the alkyne into alkene, and Lindlar's reagent is obviously hydrogen gas, palladium, barium sulfate, quinoline, and we heat it. There's a delta here as well. Here is another reaction we can do with alkynes. It is hydrohalogenation, and as we can see, we have a lot of reactions which are analogous to that of alkenes. So yeah, it's rather convenient. Here, this carbon, which is bonded to the methyl group, forms a more stable carbocation than that of this, which is bound just to a hydrogen. And this is done because this happens because of the inductive effect. And yeah, so if we were to add an alkyl halide like hydrogen bromide, the bromine, it adds to this carbon while the hydrogen adds to this carbon, and it will form a geminal dibromide over here as follows. We can obtain the anti-Markovnikov product of it by adding hydrogen peroxide as well, in which case it undergoes the free radical mechanism to achieve this product. Here's another reaction we can do, which is basically the bromination of it. If we were to add Br2CCl4, basically 4 bromines will be added to the alkyne, like 2 for this carbon, 2 for this carbon, and it will produce this. If we were to do so with bromine and water, then here we have the carbon which is bound to a larger alkyl group, so the inductive effect is higher. This carbon forms the most stable carbocation, and hydroxide ions will bind to that carbon, while the bromine atoms bind to the other carbon to produce this product. But this product is very unstable. Geminal diols, they don't exist because they are very unstable, and it will immediately dissociate to form this carbonyl group, and this is the product that is formed if we were to add bromine and water into an alkyne. Here's another thing we can do. This thing is called Clemmensen reduction. what happens is we add dilute sulfuric acid with mercuric ions in under 60 degrees Celsius, and what happens is that the alkyne group converts into a carbonyl group as shown over here to produce a ketone. It's a really convenient reaction. Actually, it's pretty useful. This is what happens when we add Bayer's reagent to an alkyne. As we probably guessed by now, two hydroxide ions will be added to this one, and two hydroxide ions will be added to this carbon. But as we know, as we have told earlier, geminal diols are unstable, so it will immediately dissociate into this group to form like two carbonyl groups in the same compound adjacently. If we were to have a terminal alkyne as so, and we oxidize it under acidic conditions, we get carbon dioxide and water. No, it's no buts. But if we have an alkyl group bound to a carbon adjoining one end of the triple bond, that part will be converted into a carboxylic acid, as shown over here. Now, these are reactions that terminal alkynes can undergo. Terminal alkynes are alkynes which have a hydrogen bound to one carbon bound to the triple bond. If we were to add sodium into the terminal alkyne, it will produce the alkyne salt of sodium as follows, while liberating hydrogen gas as well. If we were to do so with sodamide, what happens is that the same sodium salt is produced and ammonia is evolved instead of hydrogen gas. If we were to add Tollens reagent, which we saw earlier is ammonical silver nitrate NH3/AgNO3, then we get this white precipitate. Basically, this H is replaced with a silver atom and it is a white precipitate. This is a convenient identification test for alkynes, terminal alkynes specifically. And we can do so with this reagent, ammonical cupric chloride. And it produces a red-brown color precipitate as shown over here. If we were to add a Grignard reagent into a terminal alkyne, the R- group, this R- alkyl group, it will join with this hydrogen to produce an alkane, as we remember, and the rest will produce this group over here. If we were to add potassium ammonia into a terminal alkyne, the hydrogen will be replaced with a potassium atom as shown over here. Now these are reactions that are shown by the sodium salt of a terminal alkyne. If we were to add water into that salt, we retrieve the old alkyne again, and we see we see sodium hydroxide being produced as well. You see the H of this goes to here, the OH binds with of the water binds with sodium to form sodium hydroxide. If we do it with D2O, we are pretty much the same thing, except we have deuterium here instead of hydrogen. If we were to add alkyl chloride into the sodium salt of the terminal alkyne, what we notice here is that the alkyl group will be joined to the triple bond carbon, while the sodium will bind to chlorine to form sodium chloride. These are the reactions that are shown by this compound. This compound will be produced by adding a Grignard reagent into the terminal alkyne. And what we can do with it is that if we were to add water into it, we retrieve the old terminal alkyne and we get this hideous compound, HOMgCl. If we were to add heavy water, in which the hydrogen is replaced with deuterium, we get pretty much the same. We get this compound, and then we get this hideous compound that does not deserve to exist. If we were to add an alkyl halide into this compound, we will see that the alkyl group will bind to the triple bond carbon to produce this beautiful alkane, while the MgCl group will bind with the Br to form this compound, which at least is somewhat aesthetic. And these are the reactions of alkynes.